Welcome to the unit Non-Parametric Methods, presented to you by Timothy Kabue from the School of Pure and Applied Sciences, Department of Mathematics and Physical Sciences, Mount Kenya University. Welcome. Non-parametric methods in statistics, it comprises of two stages. The first stage is data correction. After data correction, the ultimate aim is to make conclusion about the population. And in the process of making conclusion about the population, we have two stages also, that is estimation of population parameters and test of hypotheses. Welcome. In this unit of non-parametric methods, we shall look at three methods of analyzing or testing hypotheses using non-parametric methods. That is sign test, Wilcoxon sign rank sum test, and Mann-Whitney U tests. In the estimation of population parameters and test of hypothesis, we are under the second point, that is test of hypothesis. And the other test of hypothesis, we usually have two categories of test of hypothesis, that is parametric statistical tests, where the sample data that we are dealing with is postulated to have come from a population whose distribution is well known, save for the parameters. That is, parametric statistical tests is a model where the parameters of the population from which the sample data is drawn are completely specified with the following assumptions. That is, the observations are drawn independently. Observations are drawn from a normally distributed population, and the population have the same standard deviation. The populations may be one or two or more, and that is why we are saying that the populations have the same standard deviation, and then variables are measured at least at an interval scale, because in statistics we have four scales of measurement, that is nominal, ordinal, interval, and ratio scale, and in the order of the strongest to the weakest. So when data analysis meets all these four assumptions, then the obvious way of testing the hypothesis is through parametric statistical tests. Some data is known to violate, or we may have some very little information concerning the population from which we have sampled. So we resort to non-parametric tests, and the model does not say much about the population from which the data is drawn, only maybe that the population is continuous. So it is applicable when the population from which the sample data is drawn is grossly violates the assumptions of parametric tests, which we have already discussed, and also on top of that, the data is spherically skewed, non-normal, of small size, and observations are measured using the weaker scales of the nominal and the ordinal scale. There is at least one parametric test for each of those. There is at least one non-parametric test for each parametric genotype, which fall into the following categories. Test of difference between groups, where we have independent samples, and then test for dependent samples, samples which are dependent. Say, for example, we have a group of students whom we have given a tutorial as an entrance exam, and then after tutorial, we still give them another exam of equal standard, and then later on, we see whether we want to test whether the tutorial has been effective. And also then we have tests of relationship between variables. So when we are talking of relationship between variables, we could be imagining about a group of subjects who have been administered a drug, and another subject has been administered a placebo, and we want to test whether the drug really works. So these tests, they fall under sign test, Wilcoxon sign rank test, and Mann-Whitney tests, and then we also have the chi-square test for independent of attributes, among others. For this lesson, we shall only look at three examples concerning sign test, Wilcoxon sign rank sum tests, and Mann-Whitney U-test statistics. Sign test procedure. The observations we are having is a sample of n observations, which we denote with x1, x2, up to xn, and these observations could be paired observations, or differences. As I have already said, we would want to take, for example, in the tutorial case, where a group of students, the same students, have been given an exam, and then we want to see whether tutorial works, so we give them a tutorial, and then we give them an exam of equal measure, and then what finally we shall have is to subtract the score of the student from the first entrant exam from the exam of after having taken a tutorial. So the null hypothesis is that the population median is equal to some value, mu naught. So in every statistical problem, we have an assertion about a population parameter. So in our idea, we are trying to find out whether there is a difference between tutorial and before the students entered for the exam. So well, the alternative is either the median is higher or the median is lower. So this is how we denote the null hypothesis, the population mean. The hypothesis will always be concerned about the population characteristic, not the sample, and we have a specific or a known median that we are talking about for that population, where the alternative is either greater or less or equal to, mathematically represented as such. So we have H, the alternative hypothesis. The median is greater than the median we have postulated, or the median is less than the median not, or the median is not equal to. When we talk of not equal to, we mean it is non-directional. It could be greater, it could be less. Now, suppose that the S plus of these observations are greater than mu naught. So we have a set of data. We have marks for subjects. These are subjects, 1, 2, 3, 4, say for example, and these are the marks. Then after, this is before, and then after. So this is, say, y1, y2, y3, and y4. Then we have the difference. So it is y1 minus x1, and so forth. So the idea is the median is equal to a particular value that we are hypothesizing, and we want to see if really the students who scored higher and those who scored lower between the two exams are the same. That is, we have equal number on either side. Then we have the S plus. So if this is our median, then every score, the differences will have a minus or a plus sign, and we shall have S plus observations with a plus and others with S minus. But generally, the S plus and S minus should be equal to the sample size that we are dealing with. Now, suppose the S plus observations are greater than mu naught and S minus are smaller than mu naught. In case where the sign test is being used, in place of paired t-test would be equal to 0. So the median is equal to 0. Values of x for which are exactly equal to mu naught are ignored. Yes, and we may have some values that will be equal to our mu naught, so that the difference is equal to 0. So we do not have a sign in that case. We shall have others which are higher than the mu naught and others that are less. So we do not have a sign. In that case, we drop that value. And that one might end up reducing the sample size lower, down, and affecting the power of the test. So what we do, or what is recommended, is that if we have odd number of ties where we have, say, x2 minus x1 is equal to 0, so we do not have a sign, then we drop that observation. And that is one way. Another way, so that we safeguard the power of the test, is to make sure that if we have even number of ties, then if we have even number of ties, then we assign half-half to positive and negative. Values of x which are exactly equal to mu are ignored, but this may reduce the sample size drastically. So we have indicated that for even number of ties, we allocate half to negative and half to positive, and for odd, we drop 1 and follow the procedure of the even ties. The sign tests. The sum of s plus and s minus may therefore be less than n due to dropping the ties, and therefore we will denote it by a reduced sample size by n naught after sorting the ties. And under the null hypothesis, we would expect half of the xi's to be above the median and half to be below. Hence, the random variable s of the signs follow a binomial distribution. Binomial distribution. And the density of binomial distribution is as indicated, where this is the procedure for getting the probabilities. So for, say for example, the probability x equals to x, where x is the random variable and x is the realization, is simply the fx, which is equal to this density here. Say for example, if we have n observations, and we want, say for example, where say take n equals to 5, and we want the probability of 2 occurrences of success, where x is success, and we have binomial distribution concerns a situation where we have only two mutually exclusive events, such that when one occurs, the other one does not occur. Say, for example, tossing of a fair coin. We have only two possibilities, either head or tail. If the coin, for example, is tossed 5 times, what is the probability of getting 2 heads? That is simply 5. We combine the 2 heads. And since if the coin is fair, we know the probability of head and tail are supposed to be equal. They are equal probable. So that is the probability of head. And then the probability of tail must be 1 minus that, which is 5 minus 2. That way. That is the probability. We can also find the probability of either less than or equal to 2 heads. So this is the probability of either 0 or 1 or 2, like that. And that is the case, then we need to add all the probabilities. And this addition is simply equal to x from 0 to 2 and 5, our number of tosses of the coin, and the successes we expect from every toss for 5 times, then a half x, a half n, or 5 minus x, like that. So that is the density for binomial. That is the pluses and minuses follow binomial distribution, and the density of binomial is given as such. So the rejection procedure would be to reject the null hypothesis of the median equal to a particular value when S is greater than a particular critical value, which we denote by Bn alpha, where alpha is the level of significance and n is the number of trials. So as we have said on this other side, the number of observations is what we also refer to as trials. It is expected that the students are familiar with binomial density, and therefore we have alpha is equal to that. So the p-value is the probability that the random variable S plus is greater than the number of the plus signs realized, and therefore we shall obtain it by summing up, just like we have summed on this tossing of the coin 5 times and determining how many or what is the probability of getting less than 2 outcomes of success. Then we note that when n is large, we resort to parametric tests and apply the Z tests. It's a fact that when n approaches infinity and p is less than 0.05, the binomial distribution tends to normal distribution, and the mean is equal to NP is equal to NP, so that we can easily now approximate we can resort to parametric tests instead of non-parametric tests if the sample size is large. Remember, we had said that these non-parametric tests apply when the sample size is small. So the Z test statistic is simply the normal minus mu sigma over root n, where x bar is the sample mean. This is the population mean denoted by NP, and sigma over root n. This is the standard error of the population, or the standard deviation, and this is the sample size. That is what the distribution will result to when Z is huge. And therefore, we can also state the non-parametric test for the median as simply the null hypothesis, the probability of a number of observations being higher than the postulated median is a half, and the other half is the alternative that is either greater, it can also be less, or it may not be equal to. The summary for testing non-parametric using the sign test, we have the various hypotheses. This is the null. It is always about the population parameter, and the alternative here is greater. We call it a one-tailed test because the critical region usually obtained from tables worked, and if this is the distribution that we are dealing with, then we have the critical region is on the right hand side. Mu is greater on that side. That is what we call right-tailed test, and it is a one-tailed test. And then we also have the left-tailed test. Mu is less than the postulated, and the p-value is obtained from that. Well, the two-sided test or non-directional test, we take the greater of the two signs, the max plus and minus, and we double the region of the critical region. We want to do an example to demonstrate clearly the points that we are putting across concerning the sign test. We have the table shows the hours of relief provided by 2 analgesic drugs in 12 patients suffering from arthritis. Now the question is there evidence that the drugs provide longer relief? Is there any evidence that drugs provide longer relief than the other? We have 2 drugs, sorry for this one. Is there any evidence that there is a better drug than the other one between drug A and B? We have 12 patients who have been administered the drugs, and in case 1, drug A relieved for 2 hours, while B relieved for 3 hours, and so forth. So what we do now, we want to test the hypothesis. So from the question itself, the hypothesis is non-directional. We have not indicated whether it is A greater than B or B less than A in terms of relieving, or the average number of hours of relief provided by the drugs. So in this case, our null hypothesis is that the median difference is 0, that the 2 drugs are the same, for relief provided by the 2 drugs is the same, and versus A is better than B, or versus these are possible hypotheses, but the question indicates a two-tailed test, whether A is less than B, B is better than. Simply we test the difference between the medians as follows. The effects from the two drugs are the same, and the actual differences tables are here. So we get B minus A, we get a positive sign. B minus A is still another positive, and until here, when we have 2.4 minus 2.6, we get a negative. So we count the number of plus signs. They are 1, 2, 3, 4, 5, 6, 7, 8, 9. And the total sample size is 12. Therefore, the null hypothesis, under the null hypothesis, S plus followed by binomial distribution with n equals to 12 and p equals to a half. If the median falls at the center, then p is equal to a half. The procedure is as follows. We choose, because our null hypothesis, our alternative hypothesis, we have said it is two-directional, and from the summary table, we take the plus, the maximum of either plus or minus, and from our table, we have realized that we have 9 pluses and 3 minuses, making a total of 12. We use the binomial tables to find the probability of observing a value of S or higher, assuming P is equal to a half and N is 12. And if this test is one-sided, then this is our p-value. But remember, in our case, it is two-sided. So the test is two-sided. We double the probability obtained in B, not 2. It is supposed to be B, not 2. We have S plus is 9, S minus is 3, N naught is 12. And therefore, our two-sided p-value from binomial table is 1.46. We can confirm this value from the tables. It is 0.073. That is, for 0.073, we have n is 12. Yeah, n is 12 is here, and the value is here. This is the value, that is, this is the probability. This is the probability. S plus is less than or equal to 3, which is simply equal to the sum. S plus equals to 0 up to n, and our n in this case is not n but 3, and then we have 12 combine n a half raised to power n, like that. That is what we are having, and if you open up this one, we are getting the value 0.073, which we have doubled to get 0.146. We would conclude that there is no evidence for a difference between the treatments at 5% level of significance, since the p-value is equal to 5, So usually, the rejection criteria is that if p-value is less than alpha, the level of significance, then we reject. Why do we do that? Why do we reject? Because it means if this is our alpha, then p being less means it is within this part. This is the area. P indicates the area above above the critical region, and this is a value Bn alpha, like that, and therefore it indicates that it is in the critical region, and therefore we reject H naught and conclude that the two drugs are different. We could conclude that there is no significance evidence between the two, and we fail to reject. We want to do an exercise. As psychologists want to know if man case prefers simulation of brain area A to simulation of brain area B. And 14 letters man K are taught to place 2 bars. When a light comes on, places on bar 1 always results in simulation of area A, while places on bar 2 always results in simulation of area B. If after learning to place the bars, the monkeys are tested for 15 minutes, during which time the frequencies for the 2 bars are recorded and the data are shown as below. We test the appropriate hypothesis. The part of the question that indicates the type of the alternative that we require is the objective of the test. Want to know if the monkeys prefer simulation of area A or area B. So that is an exercise. We look at another method, Wilcoxon sign-lang tests for 2 independent or repeated measures. So one problem with the sign test is that it discards a lot of information about the data because it only deals with the signs of the differences between the values. We need to take care of the magnitude of the values or the differences. Only the direction of the differences is concerned, but not the magnitude of the difference of a pair of scores. The Wilcoxon sign-lang tests is another non-parametric test that can be used for 2 repeated or correlated measures when measurements is taken at least at ordinal level. But unlike that sign test, it takes into account to some degree at least the magnitude of the differences. We consider the monkey preference of brain simulation area with a number of bar places in brain simulation experiment with the difference in scores ranked by absolute value. And we require to sort this on the basis of their absolute values. So we have the subject monkeys, we have the number of time within that 15 minutes that the subject monkey or monkey number 1 pressed the bar 1 20 times and bar 2 40 times. When it meaning that within these 20 times that it pressed bar 1, then it is the area of brain A that was simulated by the right, and the different light also simulated area B, and therefore that resulted into 40 places of the bar. So the difference between the two, once again, taking bar 2, we take bar 1, is minus 20, and so forth. The same case for the 14 subjects. So we now rank the differences. We look at the smallest difference, regardless of the sign. And 2 is the smallest, followed by 3. So we assign 1 and 2, and then 5 we assign 3. So these are the ranks of the differences regardless of the magnitude. Then we have the sum of the positive ranks. We go back here. So these are the positive ranks. We have positive. These are positive, positive, positive. So the sum of the positive ranks is 1 plus 2 is 3, making 6. The idea behind the Wilcoxon sign-lang test is that if you have n subjects, or observations, and suppose take